Welcome to this explainer on thermal physics. Today, we're going to dive straight into a virtual laboratory to unpack exactly how energy moves, how it's stored, and how it changes temperature. Let's get right to work.
To keep things perfectly structured for us, we'll be visiting 3 distinct lab stations today. First up, specific heat capacity. Then we'll map out cooling curves, and finally, we'll tackle conduction and radiation.
All right, let's start at Station 1, specific heat capacity.
So, we're looking at a pretty fundamental question here. Why do different materials, like your everyday cooking pots, heat up at completely different rates? The answer entirely comes down to specific heat capacity. By definition, this is the energy required per unit mass per unit temperature increase. Basically, materials with a high value require a massive transfer of energy to raise their temperature. Take water, for instance. It has a super high specific heat capacity. But low-capacity materials, like an aluminum pan, they take very little energy to heat up. So if you have identical masses of both, the pan is going to heat up way faster than the water inside it.
Now, here's the crucial formula that ties all this together. C represents our specific heat capacity. You calculate it by taking the energy transferred, that's our delta E, and dividing it by the mass, m, multiplied by the change in temperature, which we call delta theta. Getting a grip on this relationship between energy, mass, and temperature change is absolutely crucial. It allows us to perfectly measure how different materials store thermal energy. And just as a quick reminder, our final calculated answer will always be in joules per kilogram degrees Celsius. Now, before we actually calculate anything, we really need to set the scene with strict lab safety. We are going to be handling high wattage immersion heaters and boiling liquids here. It's a non-negotiable first step in any physical lab space to make sure hot liquids and solids are set in a secure, safe position. You have to handle them with extreme caution to avoid accidental burns.
Okay, safety covered. This setup brilliantly illustrates our 2 parallel experiments. On one side, we're heating 1 kilogram of water in a calorimeter, and right alongside it, we're heating an aluminum metal cylinder. Check out the specific apparatus we need to get completely accurate readings. We've got a 12-volt power supply, an electric immersion heater, and a highly sensitive thermometer. Notice how we insert a 50-watt immersion heater fully into the central hole of the aluminum block? That is to maximize thermal contact and ensure every bit of that energy goes directly into the metal itself.
By following these precise steps and strictly isolating our heating time to exactly 5 minutes, we can perfectly measure the energy transfer in both the liquid and the solid. First, we record the initial temperature, start the timer, and switch on the heater for exactly 5 minutes. Now pay close attention to step 3, because this is where the clever scientific methodology comes in. We turn off the heater, but we wait until the temperature completely stops rising before we record the highest temperature. Why do we do that? Well, because thermal energy is actually still transferring from the hot heater core into the block even after the power is cut. If you don't wait, your data is going to be skewed.
We then take all those findings and log them into an observation table like this one. This gives us every single variable we need to calculate the specific heat capacity. The table headers clearly outline our measurements with their correct units, which is super important. Time is logged in seconds, temperature in degrees Celsius, and energy in joules. Now for the total energy supplied, we calculate that as power multiplied by time, or P times T. It's absolutely vital here to convert our 5 minutes of heating into 300 seconds, so our final calculation aligns perfectly with the formula we looked at earlier.
Let's keep moving. Welcome to Station 2, cooling curves.
Here we're shifting gears. Instead of heating things up, we're going to watch them cool down until they reach thermal equilibrium with their environment. We test this by pouring 200 cubic centimeters of hot water into 2 different beakers. One is a narrow 250 cubic centimeter beaker, and the other is a much wider 500 cubic centimeter beaker. We then record the temperature drop every 30 seconds. If we map the temperature of both dropping over 10 minutes, a very clear trend emerges. The water in the wider beaker cools off much more quickly. And the reason? The larger diameter means a greater surface area is exposed to the air. A higher surface area to volume ratio drastically increases the rate of energy transfer to the surroundings. It's literally that simple.
But to ensure our cooling curves are actually accurate, we have to ruthlessly control our variables. We want only the exposed surface area of the water dictating the heat loss. If we don't wrap insulating material around the sides, or if we accidentally expose one beaker to a draft, the whole experiment becomes invalid. We've got to keep the beakers away from moving air, and we even have to warm both glass beakers with hot water before starting. That prevents any initial, rapid thermal conduction straight into cold glass.
So, as you're mapping this temperature against time, you have to ask yourself a key question.
Does the curve drop steeper when the water's near 90 degrees or as it approaches room temperature? Well, the reality is that the rate of cooling isn't constant at all. Water cools much more quickly at higher temperatures. The curve is going to be steepest at the very beginning because the temperature difference between the hot water and the ambient room air is at its absolute maximum. Then, as thermal equilibrium approaches, the rate of cooling naturally slows down and you'll see our curve flatten out over time.
Finally, we arrive at Station 3, conduction and radiation.
Now we need to actually visualize the mechanisms and pathways thermal energy takes to transfer. Let's start with conduction, which requires solid matter. We arrange 4 different metal rods, aluminum, brass, iron, and copper in a fan shape over a Bunsen burner. Now, we already know that metals are generally good thermal conductors. They transfer energy fast, whereas insulators, like a piece of wood, transfer it incredibly slowly. But in our lab today, we want direct scientific evidence to rank these specific metals based on their actual thermal conductivity. The method we use here is just beautifully simple. The rod that drops its wax first gives us instant visual proof of which metal is the superior thermal conductor. Here's what happens. Thermal energy from that central Bunsen burner conducts outward along the metal rods. And guess what? The identical wax blob on the copper rod ends up melting and dripping first. This happens because copper's internal lattice structure is just better at transferring kinetic energy efficiently than aluminium, brass, or iron. So, the shortest recorded time to melt the wax is our definitive proof of the highest rate of thermal conductivity.
Next, we test radiation, which is fascinating because it needs absolutely no matter at all to propagate. We take 2 identical thermometers, one painted a dull black and one left shiny. We heat them both up in hot water and then clamp them in the open air. This is such a brilliant experiment because it completely isolates infrared radiation from conduction or convection. Since radiation doesn't require matter, all objects emit it, but the surface finish and color, that drastically changes the rate of the emission.
So both of these start at the exact same temperature and are carefully shielded from drafts. Which surface do you think sheds its infrared radiation faster? The dull black one or the shiny one? Remember, the thermal energy is being transferred to the environment purely as infrared radiation. Because we warmed them both to the exact same starting point in the beaker, any difference in their cooling time is 100% down to that surface finish.
And the data doesn't lie. It perfectly proves that the black bulb plummets in temperature much faster. This demonstrates that dull, dark surfaces are just incredible emitters of infrared radiation when you compare them to shiny ones.
Now, taking everything we've uncovered across these 3 lab stations, I'm going to leave you with a real-world puzzle to solve for your own home. If dull black surfaces are the absolute best emitters of infrared radiation, and water has an incredibly high specific heat capacity, which, by the way, is exactly why it's used inside pipes to carry massive amounts of thermal energy, what color should the outside of your radiator be painted to heat your room most efficiently? Think about it. Thanks for joining me for this explainer, and I'll catch you next time.